Students, in the previous video, we have seen deriving two frequency domain specifications, that is MR and omega R. That is the frequency at which the maximum value of closed loop transfer function will occur. That is what is called as a resonant frequency. So we have found out that resonant frequency expression and also the resonant peak expression. Okay, so those two things we have seen in the previous video. In this video, we will continue deriving some more frequency domain specifications. So as I said, MR expression and omega R expression we have found in the earlier video. So in this video, we will be deriving first bandwidth frequency, okay, omega B. So bandwidth frequency is the frequency at which magnitude of closed loop function is 1 by square root of 2 or minus 3 dB. So when you convert this magnitude value 1 by square root of 2 into dBs by applying 20 log of, you will get minus 3 dB, approximately minus 3 dB. So if you are going to have the magnitude of the closed loop transfer function in decibels, then you have to equate it to minus 3 dB. If you are going to have it as such the magnitude, you can equate it to 1 by square root of 2. So now we should have in hand the magnitude of closed loop transfer function, which we have derived. So we have that M expression. We have seen in the previous video, we have taken a closed loop transfer function of a second order system. We have also found the magnitude and phase of the second order system, isn't it? So now I'm going to equate the magnitude function, that is M, and to 1 by square root of 2. So you can see here, this is the expression for M. Okay, in the previous video we have seen the expression for M and alpha. If you remember that, then it is easy. So now we are going to equate that to 1 by square root of 2. Okay, after this it is purely mathematical reduction. So you do some mathematical reductions to find the frequency at which the magnitude is equal to 1 by square root of 2, that is bandwidth frequency. Now I have, instead of writing U, I am going to include the suffix B, because this is the frequency at which, this is the frequency, UB is the frequency at which the magnitude is equal to 1 by square root of 2. So instead of writing frequency, I am going to write it as bandwidth frequency, okay, UB. So now cross multiply, bring all the terms to left hand side, okay, you will get a function like this, which is having highest power of 4. So to solve this equation, of course we have to introduce another variable, so that x, I am introducing x here, x is equal to ub square, so that I can bring down this equation to quadratic equation format. Okay, so x is equal to ub square, this is a variable that I am introducing. Now this expression becomes x square minus 2 into 1 minus 2 tau square into x minus 1 is equal to 0. Okay, so this is a quadratic equation. You can solve this quadratic equation and get the value of x by using the formula x is equal to minus b plus or minus square root of b square minus 4ac by 2a. Okay, so students can try this and find the x values. So you will get two roots plus or minus. Okay, so we are getting two roots, x is equal to, one is with plus sign and the one is with minus sign. Okay, since frequency cannot be negative, we are not going to take this root with negative sign. We are going to take only root with this plus symbol. Okay, so we will consider only x, one value of the root. Okay, so once you have found the x value, you have to find now ub. Okay, ub. So x is equal to ub square, or ub is equal to square root of x. So now I have found ub. ub is equal to square root of this x. Okay, so students can take some time for getting this expression, that is cross multiplying and bringing all the terms to the left hand side. Okay, so after finding ub, okay, ub expression is here. You know that normalized frequency is always like frequency by natural frequency. So to get omega b, okay, ub has to be multiplied with omega n. Okay, omega n. So frequency by natural frequency is normalized frequency. In the earlier video also we have seen that resonant frequency divided by natural frequency is equal to U suffix R. Okay, normalized resonant frequency. So now here to get the bandwidth frequency by natural frequency will be equal to normalized bandwidth frequency UB. Okay, so since we know UB, you multiply it with omega n, you will get omega B. Okay, omega B, this is bandwidth frequency in radians. Okay, radians per second. So just we have got to take this expression and multiply it with omega n. Okay, so this is the final expression for bandwidth frequency, which is bandwidth frequency is in terms of tau. Okay, the variable is tau and natural frequency. Okay, so this is the expression for bandwidth frequency. So after deriving this bandwidth frequency, we will now go and find phase margin, which is another frequency domain specification. So phase margin gamma. Okay. Phase margin, in the previous video we have defined what is phase margin. Phase margin gamma is equal to 180 degree plus 5 GC, that is phase at gain crossover frequency. Okay, so the first step becomes you have to find the gain crossover frequency. So the definition for gain crossover frequency is what? Is it is the magnitude of open loop transfer function to be equal to 0. The frequency at which magnitude of open loop transfer function is equal to unity. That is what is called as gain crossover frequency. Okay. So now let us go and find the gain crossover frequency first, and then apply that gain crossover frequency in phase and find the 5GC. So now I am going to take the open loop transfer function. Actually by definition itself the gain crossover, just go back to the previous video and see gain crossover frequency, you have to consider open loop transfer function. Okay, so open loop transfer function of second order system is omega n square divided by s into s plus 2 tau omega n. Whereas closed loop transfer function for second order system is omega n square divided by s square plus 2 tau omega ns plus omega n square. So now we are, as per the definition, we are considering only the open loop transfer function. Okay, in open loop transfer function, after substituting s is equal to j omega, you will get an expression like this. Okay, as usual, divide the numerator and denominator by omega n square. So you will get an expression like this. So we already know that any frequency divided by natural frequency will be normalized frequency u. So instead of writing omega square by omega n square, I will write it as u square. Okay. So I will get the open loop transfer function in terms of u now. Okay. So now we have got to find the frequency at which this open loop transfer function is equal to, that is the magnitude of this open loop transfer function is equal to 1. Okay, so what is the job now? After getting g of j omega, this has to be converted into magnitude and phase. Okay, magnitude and phase, and that magnitude has to be equated to 1 so that you get the gain crossover frequency. So you can see that here the magnitude, so I have split that into two terms. One is magnitude, another one is phase. So magnitude is this function and phase is this one. I have just used square root of a square plus b square tan inverse of b by a. Okay, for the expression g of j omega. So after getting magnitude and phase expressions, to get gain crossover frequency, this magnitude has to be equated to 1. Okay, if it is in dBs, it can be equated to 0 dB. Now I am not converting it into decibels, it is now I am taking magnitude as such. So I am going to equate this to 1. When I equate this expression to 1, the frequency at which this thing happens, that frequency is called as gain crossover frequency. So I am equating this to 1 and I am writing the frequency's name as not just UGC. Okay, this is the frequency at which the entire magnitude becomes 1. Okay, so that we have done, and now it is only simple mathematical reduction. As I said, you will get it a simple expression, but the power is 4, so we have to take another variable x, so that UGC square is equal to x. So after applying x is equal to UGC square, you will get x square plus 4 tau square x minus 1 is equal to 0. This is a quadratic function. So solving this quadratic will be easy for you. Okay. After getting the roots, you will get the, that is you will get the roots value. That will be the x value, isn't it? X is equal to minus b plus or minus square root of b square minus 4ac by 2a. So let me show you the values of x. Only one value we have taken with positive root. Okay. After getting x, UGC is equal to square root of x, or x is equal to UGC square. Okay. So UGC is equal to square root of x. We have taken square root of this x value. This x value, so that we got the UGC. So this UGC is nothing but the frequency at which gain of the open loop transfer function is equal to unity. After getting this frequency value, you have to find phase at this frequency. I will tell you where is the phase function. See, this is the phase. This is the phase of the open loop transfer function. So we have to find the phase value at what frequency? At gain crossover frequency. That means you have to substitute here gain crossover frequency. Okay, when you substitute here gain crossover frequency, you will get phase at gain crossover frequency, that is phi GC, phi suffix GC. Okay, so here you can see that phase margin is 180 degree plus phase of G of j omega at u is equal to UGC, or omega is equal to omega GC. So as such, I have substituted the phase function here, but instead of 2 tau by u, isn't it? Instead of u, I have substituted here UGC value. Okay, UGC value, UGC. Okay, so now this is the expression for phase margin. Phase margin is equal to 180 degree plus phi GC. That is phase of open loop transfer function at gain crossover frequency. Okay. So this is phase function only. I've got it from here. Function. So we have got a phase margin now. So gain margin, if you remember gain margin definition, it is 1 by magnitude of open loop transfer function at phase crossover frequency. So now our job is to find phase crossover frequency. Phase crossover frequency is nothing but the frequency at which phase is equal to minus 180 degree. Okay, so now this is very simple thing. I will show that for a second order system it is infinity. Okay, for that let us go and find phase crossover frequency. Phase crossover frequency is nothing but phase of open loop transfer function is equal to minus 180 degree. So I will equate this phase to minus 180 degree. So what will happen? Tan goes that side, so tan 180 degree is 0. So UGC, sorry, UPC, that is phase crossover frequency. The frequency at which this thing happens will be 0. After getting the frequency at which the phase is equal to minus 180 degree, that is you will get UPC, that is UPC, phase crossover frequency, as 0, and when you substitute this phase crossover frequency in magnitude, you will get it as 1 by 0 infinity. Okay, so gain margin kg is equal to 1 by g of j omega at pc. Okay, so 1 by infinity, again it is going to be infinity. So it is a simple derivation, that's why we have not done it. It is gain margin of second order system is always infinite. Okay, it is always infinite. Once again reiterating, kg, that is gain margin, is equal to 1 by magnitude of g of j omega at pc. So you will get phase crossover frequency as 0, because when I equate this phase is equal to 1 minus 180 degree as per the definition of phase crossover frequency, it is the phase of the open loop transfer function is equal to minus 180 degree. When I do that, that frequency will be 0. When I take that frequency and substitute in this magnitude, I will get the magnitude as infinity. Okay, so kg is equal to 1 by this magnitude. Am I right? As per the definition, kg is equal to 1 divided by magnitude of g of j omega. So 1 by infinity, you will again get it as infinity. So that's how you got it as this gain margin as infinity. Okay. So in this video, we are winding up with all the frequency domain specifications. Okay. So far we have derived all the frequency domain specifications such as resonant peak, resonant frequency, bandwidth frequency, phase margin and gain margin. Okay. And of course, these things we have done it for second order system. In the next video, we will see what is the correlation between time and frequency response. Okay, time and correlation between time and frequency domain specifications. Okay, that we will see in the next video.